Hi everyone, and welcome to JP Academia. MRI or magnetic resonance imaging is a medical imaging modality that do not use ionizing radiation that includes X-rays or gamma rays and is considered a non-invasive procedure. Instead, MRIs use a strong magnetic field and radiofrequency waves to take pictures mostly of your brain. The MRI scanners is mainly metal cylinder surrounded by a strong magnetic field. Thus, understanding the basics of electromagnetism is important to study MRI. Let's start the lecture. This is the outline of this lecture. Let's start by discussing the magnetic properties of matter. The magnetic properties of matter is considered as a fundamental property of nature. The magnetic fields are essentially produced by electric currents, meaning any current that can be macroscopic currents in wires or microscopic currents associated with electrons in atoms. Both the electric field, so this one, and the magnetic field contribute to the Lorentz force as shown in this formula. The electric force is shown with this charged parallel plate setup with a certain voltage source here. The direction of the force depends on the direction of the electric field E and the sign of the charge shown here. The force for the magnetic force, as illustrated here at the right, follows the right-hand rule. The force is perpendicular to both the V and the B, the magnetic field, going into the page for this scenario. So that's the direction of the force. We have here some examples of magnetic field sources such as current carrying wire, or let's say a loop of wire with current, or a solenoid, this one, a bar magnet, or the earth itself. Okay, now let's go to the static and dynamic magnetic fields. Static magnetic fields are related with a permanent magnet and is due mainly from the total angular momentum of electrons within these materials. Lone electrons have a quantity called the electron spin S, shown here, and this is inherent and it comes from the revolution of electron around its own axis, shown. In addition, electrons orbiting a nucleus also have this quantity called the orbital angular momentum L. This comes from the revolution of electron in specific orbits around the nucleus. Both these angular momentums are quantized based on quantum mechanics, thus we can sum these two quantities as shown to get the total angular momentum J, also shown here in the illustration. Next, we will describe dynamic fields. The connection between electricity and magnetism started in an experiment observed by the physicist with the name Hans Ørsted, where he noticed a deflection of a compass, let's say, we have here, near the current carrying wire in his laboratory. Then in the year 1986, Ampere formally described the relationship of current and magnetic field strength generated. So we have here the Ampere's law in its original formulation. It states that for any closed loop path, the sum of the length elements, dl, times the magnetic field B in the length direction is equal to the permeability times the electric current enclosed in the loop. Next, a changing magnetic field also induces electric current. And this was described by Faraday by measuring a voltage in a coil of wire by moving a magnet into it. So we have a permanent magnet moved in a current carrying wire. Faraday's law of induction states that the line integral of the electric field around a given closed loop is equal to the negative rate of change of the magnetic flux, this one, through the enclosed loop area as illustrated here. In discussing the electromagnetic theory, we have these four Maxwell's equations. It mainly describes how electric charges and currents create electric and magnetic fields. Maxwell's four equations can be stated as follows. First, we have this equation, the Gauss law for electricity. Wherever a charge exists, an electric field diverges from it or into it. Therefore, the area integral of the electric field provides a measure of the net charge enclosed in that area. Next, we have this second equation, the Gauss law for magnetism, and it can be stated as the magnetic field lines B can only exist in closed loops, unlike your electric field. This also implies that there are no magnetic monopoles or those magnets that are purely north pole or south magnetic pole. Third, we have this equation. This refers to the Faraday's law. An electric field E is produced by changing magnetic field dB over dt, and this is also the basis for electric generators and transformers. And last equation, we have this one. This is the Ampere-Maxwell's law, and can be stated that either a constant current, this one, or a changing electric field creates a circulating magnetic field. This equation is also used in calculating magnetic field for certain geometries. In discussing magnetic fields, we will encounter these two units. First, we have the Tesla. Second, we have the Gauss. Tesla is an SI unit of magnetic field, which can be expressed as the force per unit length exerted on a current carrying wire, as shown in this unit. 1 Tesla is equal to 1 Newton per ampere meters. Then we have Gauss. Gauss is the unit of measurement for magnetic field in the older CGS system, or centimeter gram second system. This is used in describing smaller fields that includes gradients, RF coils, or fringe fields. 1 Tesla is equal to 10,000 Gauss. Now, if we are going to compare the magnetic field magnitude of a clinical MRI machine with the Earth's magnetic field, which is about 0.5 Gauss, 3 Tesla MRI, let's say, is around 60,000 times stronger than the Earth's magnetic field. While we have here other sources, such as a neuron depolarization with an approximate value of magnetic field of 0.5 picotesla. For clinical MRI, that's 0.5 to 3 Tesla, while for laboratory NMR spectrometers, it has a value of 6 to 23 Tesla. NMR spectroscopy, as mentioned here, can be used in quality control and research, mainly to determine the content and purity of sample. Next, you will usually hear the term gradient when talking about MR imaging. It can refer to this two gradient in MRI. First, the magnetic field gradient, and second, the gradient coils. A magnetic field gradient refers to the variation in magnetic field magnitude or direction between 2 points, as shown in the drawing. So let's say this point we have 1 Tesla, at this point we have 1.005 Tesla, and the length here, or the distance, is 1 meter. Therefore, we can have this measurement of gradient using this formula. So about 5 millitesla per meter. On the other hand, gradient coils refer to a set of electromagnets embedded in the body of the MR magnet assembly. It is used to spatially encode the positions of protons by changing the magnetic field linearly across the imaging volume. So we have these three sets of gradient coils used in almost all MR systems. So we have X, Y, and Z gradients. For a more detailed discussion of magnetic field gradient, note that your magnetic field B is a vector quantity, so that has magnitude and direction in space, and we have this components along the Cartesian coordinate system. Thus, we can express the components as shown. The gradient of magnetic field B can be expressed using the del operator, this one, shown here. And the del operator of B is just a Jacobian, or a second-order tensor, shown here. When we say Jacobian, it is a matrix of partial derivatives of the principal components of the magnetic field. Thus, it gives us a view of all the changes of each vector component along each coordinate system or coordinate axis. If the change in the magnetic field, for example, is along the z direction only, and no change is observed in both the x and the y components, the partial derivatives with respect to x and y are all equal to 0. So we have here the term susceptibility, and it refers to a measure of the extent to which a substance becomes magnetized when it is placed in an external magnetic field. You can think that this quantity describes the ability of a material to be magnetized. When a material interacts with a magnetic field, let's see, we have this one, an internal magnetization called the polarization J, this one, is generated that either augments or opposes the external magnetic field. Thus, magnetic susceptibility can be described as the magnitude of the internal polarization J over the strength of the magnetic field B naught. So on. Materials can be classified based on their response to an external magnetic field as diamagnetic, paramagnetic, or superparamagnetic, and ferromagnetic. So on. Diamagnetic materials have a property that opposes the applied magnetic field, as shown in the drawing, but it is very weak as observable in the values of its susceptibility. Most biological tissues like water and fat are considered weakly diamagnetic. Next, paramagnetic materials is stronger compared to diamagnetic materials and generates magnetization in the same direction of the applied magnetic field B naught and is also proportional to it. Some tissues have accumulations of the metals like iron or gadolinium where the field concentrates. These tissues are considered paramagnetic, and we have this value of susceptibility, which is always positive. Last, super paramagnetic and ferromagnetic materials produces very large magnetizations greater than the applied field as observable in its susceptibility values. And super paramagnetic materials includes ferritin or hemosiderine, while ferromagnetic materials include iron and steel. So metals like nickel and cobalt, iron exhibit ferromagnetism. And ferromagnetism is a property of molecules in solid crystal or lattice. So ferromagnetic materials, the atoms, form magnetic domains, shown in the drawing or in the figure, in which arrays of electron spins become locked together in alignment. Due to the formation of the magnetic domains, and extremely large values of susceptibility psi are observed in ferromagnetic substances. In bulk materials, these domains usually cancel and it leaves the material unmagnetized. If an external applied magnetic field, on the other hand, is present, as shown in the drawing, and going upward, so alignment in the domains can be observed. Thus, application of small external fields moves the walls to form larger domains, and higher external fields rearrange these domains in the same direction and increases the net magnetization as shown. Moreover, it has a tendency to remember their magnetic history called the hysteresis, and meaning it will remain magnetized after being subjected to an external field. Permanent MR magnets are made of ferromagnetic materials such as neodymium, iron, boron. So last, super paramagnetism. So this is a material property that occurs in small, single-domain magnetic particles with no magnetic memory. I have here this table comparing super paramagnetism with ferromagnetism. When this substance is placed in an external magnetic field, it generates a strong internal magnetization due to the electrons exchange coupling within the domain, but not as great as the ferromagnetic materials because it has a single domain as stated in the table. On the right, we have here an image where super paramagnetic iron oxide or SPIO nanoparticles are used to as MR contrast label. Superparamagnetic iron oxides are a class of MR contrast agents composed of nanoparticles of iron oxide crystals coated in carbohydrates, and they are used to image vasculature and the liver. So here, this is for a whole animal coronal MRI image labeled with SPIO. Okay, in summary, the magnetic properties of matter are considered as fundamental properties of nature. It can be static or dynamic field. Maxwell's equation describes how electric charges and electric current create electric and magnetic fields. We also have this term gradient in MRI that can refer to the magnetic field gradient and to the gradient coils. Last, susceptibility. This refers to the measure of the extent to which a substance becomes magnetized when it is placed in an external magnetic field. And that's it for this lecture. Thank you. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.